Good day, everyone. So we are reviewing Wetzel's Limnology textbook. This is edition number 4, and we are on chapter 14. And right now we are focusing on nitrate reduction and denitrification. And where we left it at yesterday was on this paragraph, which presents the reduction of nitrate. So let's get started. The reduction of nitrate coupled to iron cycling also exists, which can take place through both biotic pathways mediated by microbes and abiotic pathways. The abiotic pathway was found in an aquifer with a lower anoxic zone characterized by ferrous-rich water and in forest soil. The biotic pathway might be more likely to occur in surface waters than the equivalent abiotic reaction. Global rates of denitrification have been estimated and compared across soils, groundwater, lakes, and rivers and estuaries. Denitrification in groundwater can be significant, particularly in some areas of Europe, while denitrification in rivers appears to be more important in warmer areas of the world. A caveat in this global data is that more studies have been done in Europe and North America than many other areas of the world, so this may be biased interpretation. The rate of denitrification as of nitrification decreases in acidic water. Denitrification rates also decrease with lower temperatures. When substrates, that includes nitrite and nitrate, are limited in the system, the winter denitrification rate can be higher than the summer denitrification rate, as has been found in multiple lakes in Canada and Japan. Optimum rates of denitrification occur well above the temperatures of most natural freshwaters. Rates of denitrification by nitrate, reducing bacteria in a eutrophic lake, Preußische in Germany, showed marked seasonal and depth variation. Rates of nitrate reduction were particularly high and were correlated with denitrifier cell numbers during the early portion of summer stratification before hypolimletic nitrate concentration were greatly reduced. High concentration of oxygen and low level of nitrate depressed rates of nitrate reduction, but had relatively little effect on cell numbers, especially in winter. In the Baltic Sea of Northern Europe, the denitrification was more strongly driven by the chemolithotrophic process and limited to the water layers with a nitrite coexisting with sulfide. So before we move on to the next section, let's look at this figure here. So the figure's title is the Global Nitrogen Loading and Denitrification by a River Basin. And so the model production of A, nitrogen loading in kilograms of nitrogen per hectare per year, and denitrification of land-based nitrogen sources in terrestrial and aquatic systems in kilogram of nitrogen per kilometer squared per year. Denitrification B, denitrification in soils, C, denitrification in groundwater, D, denitrification in lakes, E, denitrification in rivers, F, denitrification in estuaries. All rates are mapped as average rates for catchments. Note the difference in scale for nitrogen loading compared to denitrification. All right, so they are telling us first that we need to pay attention to the loading rates. So for the nitrogen loading, we have kilogram of nitrogen per hectare per year, where for denitrification we have kilogram of nitrogen per kilometer squared per year. So nitrogen loading to land surface, and then here we have denitrification in soil. So this is the amount of nitrogen that is inputted to the land, and then this is the amount of nitrogen that is generated out of the land, so out of the soil. So meaning by that it's the amount of nitrogen that is lost to the atmosphere from the soil. So in blue we have low values, and then in red we have high values. So the first thing that jumps out is in the area that are agricultural areas of the world, like such as the Midwest of North America. We have Western Europe, like we have France, Germany, Poland, and then England here, and then we have the Indian Peninsula here, and we have China. Those have very high nitrogen loading to land surface. In terms of denitrification, we have high values in India, as well as northern China, and then just north of the Korean Peninsula. Then we have Brazil, and then we have some areas here in North America, although not as high as in India. So, and what we also see in the Arctic areas, in the cold weather areas, we have not very much nitrogen loading because there's not that much agriculture going on, as well as there's not much ways for the biotic process to generate nitrogen, because of the fact that a lot of the land is either frozen for a major part of the year, and therefore the growth season is smaller, as well as the soils are poor. And then we have high altitude here, for example in Alaska and northern Canada, as well as in Russia and Siberia and the likes. And we see the same pattern in South America, and to some extent in southern Australia, but although the Australian continent here is probably has a low nitrogen loading because there's not much agriculture in the central part of Australia. Now, denitrification in groundwater. So this is the loss of nitrogen from groundwater to the atmosphere. So it's very high in Northern Europe, except for Scandinavia. And it's also not, I don't know, high, but it's at a value of about 15 to 25 kilogram of nitrogen per hectare per year in North America, in the Midwest, as well as Northeastern America. And then otherwise, most of the world is about at the same value. We don't have much denitrification going on in Africa, and then the like. So then denitrification in lakes. So very high value actually in the Laurentian lakes here, the Great Lakes. Very high value actually. It's the highest value of anywhere of any lakes in the world. Besides, so pretty high value, but not as high in. I guess that would be like Central Europe to Central Russia in this. And then most of the world, and after that is the denitrification in lakes is very low. Denitrification in rivers. So this is the major river basin. This is the Amazon River Basin. We have the Yellow River Basin, for example, here. And then we have the Upper Mississippi for North America. So we have a pretty high rates of denitrification in these rivers. And then we have the part of equatorial and tropical Africa with pretty good denitrification as well. Then denitrification in estuaries. So most of the world is going to have harmony of each other. There's not much going on in terms of denitrification in estuary, besides maybe like the Alpine area of Europe. So maybe this is the part of the Rhine, although there's not much of an estuary either. And then we see a little bit of denitrification in the rivers that are draining China, as well as Indonesia here, and then to some extent Bangladesh, major estuary here. As for Brazil, is the Amazon River. We don't have much denitrification in those estuary for some reason, but we do have some amount of denitrification in the estuary is located in Central America. So that's about it for this figure. Why don't we move on? Denitrification can be coupled with nitrification, resulting in low concentration of nitrate. In lake sediments, denitrification of added nitrate 15 or N15 was rapid. Within 2 hours, up to 90% of added nitrate was reduced much to nitrogen 15 gas. or dinitrogen 15 gas, I should say. Similar results were found in the sediments of several oligotrophic lakes, where denitrification in the sediments was functionally coupled to the supply of nitrate by nitrification. Much of the nitrate from lake sediments is incorporated into bacterial organic matter. These authors found that up to 37% of experimentally added nitrate became incorporated into the organic fraction. The remainder was denitrified. Denitrification rates of sediments can be 3 to 4 orders of magnitude greater than those of the overlying water within the same system. Denitrification activity within sediments of both lakes and streams is related to the macrogradient of reducing conditions. In sediments of the littoral zone or those in contact with oxygenated water, denitrification rates can be lower at the sediment surface and increase at sediment depth of between 10 to 15 millimeter, where reducing conditions increase. However, in the riparian zone in Baiyangdian Lake in China, with a groundwater level of around 50 centimeters, the denitrification rate increased with soil depth up to 100 centimeters. Denitrification rates have also been found to increase with a higher macrophyte root surface regulated by organic substrates excreted from the roots. Macrophytes can also provide suitable attachment surfaces for denitrifying bacteria, and the macrophyte litter decomposition is likely to favor denitrification via oxygen consumption and carbon source supply. Denitrification rates show diel and seasonal variations. Oxygen production by algae attached to the sediments in the light can increase the thickness of the aerobic layer and reduce denitrification in the sediment by as much as 70%. After dark, oxygen is rapidly consumed by bacterial respiration at rates faster than it diffuses when from overlying water, and denitrification again increases as anoxic and reducing conditions return. Nitrous oxide, or N2O, is an intermediate product of the denitrification pathway and is also a greenhouse gas. Nitrous oxide is usually rapidly reduced to dinitrogen, I should say, but its distribution is quite variable. Although nitrous oxide has not been found in many lakes in appreciable quantities, large nitrous oxide accumulation were repeatedly observed in the strata of greatly reduced oxygen of eutrophic lakes, concomitant with large concentration of nitrite. Although nitrification contributed to the accumulation of both compounds to some extent, denitrification was the dominant process of nitrite formation in these lakes. Rates of nitrous oxide and nitrite formation were maximal with very low concentration of dissolved oxygen and inhibited by reducing conditions in the lower hypolemnion sufficient to reduce iron and sulfide ions. In anaerobic littoral and wetland sediments, denitrification dominates as the process producing nitrous oxide, but nitrous oxides to dinitrogen ratios are greatest at low rates of denitrification. Nitrous oxide has been found to be released from aerobic riverine sediments into the overlying water or from wetlands into the atmosphere during summer months, for example, in Zhejiang Plain, China. In a series of 7 amictic, permanently ice-covered lakes of Antarctica, a detailed study indicates that nitrous oxide maxima were largely a product of nitrification and that denitrification was the sink for this gas in anoxic water. Maxima of nitrous oxide were common in depth gradient, where oxygen concentration and redox potential were decreasing, and nitrous oxide was nearly absent in anoxic zones of low redox potential. The ice barrier results in an appreciable supersaturation of nitrous oxide, some of which evades to the atmosphere through the brief period of the summer mode of open water at the edge of the ice. The process of DNRA also contributes to nitrate removal in aquatic ecosystem, but the relative importance of DNRA and denitrification on nitrate removal is quite variable between different aquatic systems. A study of a eutrophic lake in China showed that denitrification was the dominant pathway to remove nitrate in this eutrophic lake, with the denitrification rate being 7.4 to 8.5 times the DNRA rate. So before we move on to Anamox, let's look at this figure, or this table I should say, 14-5. Approximate rates of bacterial denitrification in lake and river water and sediments by direct measurements. So on the left we have the lakes, we have then the rate of denitrification and in water on micrograms of nitrogen per liter per day. In the sediment, it's in milligram of nitrogen per meter square per day. So the highest value that we have here is in eutrophic lake, between 3 to 500 micrograms of nitrogen per liter per day in terms of bacterial denitrification rates. The lowest we have quite the range though. We have here we have this lake in Sweden, where the rate of denitrification is very low, and then we have this pretty big range here between 0 and 30 micrograms of nitrogen per liter per day for a lake in Ontario. So what we see is that nutrient-poor lakes have low rates of denitrification, where nutrient-rich lakes have high rates of denitrification. In the sediments, does it follow the same pattern? Wetlands, we have very high, although the range is also very high. I mean, it's 1,000-time range. So eutrophic lake is pretty high too, but it's not as high as wetlands or rivers. Or, I mean, this is Sugar Creek that has a value rather than a range. It's pretty high. It is turbicid warm, so we can see that sediments where there is turbicid worms, we have pretty high rates of denitrification, and probably because the worms are helping to mix the sediment and therefore increase the efficiency in which the bacteria is denitrifying the sediment. And then without worms, you can see it's not as high. This lake here in Denmark has pretty high rates in the sediments. Then we see the same, somewhat of similar pattern than the wetlands for a drainage ditch in the Netherlands of 160. And then, surprisingly enough, actually, we have a pretty high rate, although I'm not sure why it's in parentheses, for Smith Lake in Alaska. And then that lake in Sweden, we also have a pretty high rate of denitrification, which is actually opposite to what we saw in terms of denitrification in water. So high rates in sediment and low rates in water. Let's see here, did they explain why we have a parentheses for that value? No, I don't see so. I think so, I don't see that. Okay, so let's start a little bit Anamox, and I'll leave you in a few minutes here. The process of anaerobic ammonium oxidation, abbreviated to Anamox, has only been described relatively recently. This process converts 1-to-1 molecule ratio of ammonium and nitrite to dinitrogen in the absence of oxygen and without the need for a carbon supply. So we have ammonium plus nitrite is equal to dinitrogen plus 2 waters. Anamox is known to be mediated by 5 genera of chemoeutrophic bacteria, that is Brocadia, Kuehnemia, Homoxoglobus, Jetenia, and Scalindua. Anamox in the natural environment was first discovered in marine sediment and in the marine water column. Recent studies have shown that Anamox also occurs in the freshwater ecosystem, for example, freshwater lakes, rivers, reservoirs, wetlands, and rice paddies. A comparison of the percentage of dinitrogen production from Anamox versus denitrification in a range of studies has shown highly variable results within systems. However, at times, this process can be significant in terms of nitrogen removal. Anamox, as with other nitrogen transformation processes, varies spatially and temporally driven by chemical and physical factors, including substrate availability, temperature, salinity, and organic carbon content. And I think that's going to be it for today. So we'll leave it here. We'll pick it up tomorrow with subsection E, nitrogen budgets in lakes and reservoir. And thanks for attending today's session on the nitrogen cycle. And I will see you tomorrow. Have a good day. Bye.